day to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on special theory of relativity, lecture number 3, in which I will describe about Lorentz and Fitzgerald contraction. Before describing the Lorentz and Fitzgerald contraction, I would like to give you some basics which will help to understand Lorentz and Fitgerald contraction. Let OX be x-axis and OY be y-axis, O be the origin. Let PQ be a straight line parallel to y-axis. Coordinates of P be x1, y1 and coordinates of Q be x2, y2. Perpendicular from P to x-axis be PA and OA equal to x1 and also OA equal to x2. Therefore, x1 equal to x2. Therefore, a straight line parallel to y-axis has x coordinates same in any points on the straight line. Length of PQ equal to square root x2 minus x1 whole square plus y2 minus y1 whole square. Here x1 equal to x2, x2 minus x2 whole square plus y2 minus y1 whole square. This is 0, this is y2 minus y1 whole square root, and this will be equal to y2 minus y1. Therefore, the length of the line PQ parallel to y-axis will be difference between y coordinates of the endpoints of the straight line. Now, on the basis of this concept, we will try to apply this concept for the solution of Lorentz-Fitzgerald contraction. Now, we describe about Lorentz and Fitzgerald contraction. Since in Lorentz transformation, we know that S prime and S be two frame of references in which axes are parallel in both systems, and also S prime frame of reference moves with uniform velocity along x prime axis. We get the Lorentz transformation equations as follow. X prime equal to beta x minus vt, y prime equal to y, z prime equal to z, t prime equal to beta t minus Vx by c square, where beta equal to 1 by square root 1 minus v square by c square. C be the velocity of light. Now let a rod of length L, which is parallel to y-axis. Let at time t1 the coordinates of one endpoint of rod x1, y1, z1 and at time t2 the coordinates of other endpoint of the rod be x2, y2, z2. Let t1 equal to t2 equal to t and x1 equal to x2, z1 equal to z2, because the rod is parallel to y-axis. Therefore, length of the rod at time t equal to y2 minus y1. This is number 1. Let at time t1 prime equal to t2 prime equal to t prime, the coordinates of the endpoint of the rod in S prime system be x1 prime, y1 prime, z1 prime and x2 prime, y2 prime, z2 prime respectively. Let length of the rod in S prime system be L prime. Therefore, L prime equal to y2 prime minus y1 prime. This is number 2. Since y1 prime equal to y1 and y2 prime equal to y2, therefore from 2 L prime equal to y2 minus y1. This is number 3. Let this length is L. Therefore, from 1 and 3 we get L equal to L prime. Therefore, if the rod is parallel to y-axis, then length of the rod in both system be same. Similarly, if the rod is parallel to z-axis, then the length of the rod in both system will be same. Now let the rod is parallel to x-axis. Then L will be equal to x2 minus x1. This is number 5. And L prime equal to x2 prime minus x1 prime. This is number 6. By Lorentz inverse transformation, we have x equal to beta x prime plus vt prime, y equal to y prime, z equal to z prime, and t equal to beta t prime plus v x prime by c square. This is number 7. Using this result, in 5 we get L equal to x2, means here beta x2 prime plus v t prime minus beta x1 prime plus v t prime, and this will be beta, this beta vt prime, beta vt prime cancel, remains beta x2 prime minus x1 prime. This is equal to beta L prime, implies that L prime equal to L by beta. This is equal to L beta, means 1 by square root 1 minus v square by c square, and this equal to L multiply 1 minus v square by c square to the power half. Therefore, L prime is less than L. 1 minus something, binomial expansion. This is number 8. This proves that the apparent length of a rigid body in the direction of the motion is reduced by the factor under bracket 1 minus v square by c square to the power half. Here we have seen. Hence, every rigid body appears to be longest when at rest relative to observer, that is L is greater than L prime. L be the length of the rod when it is at rest, and L prime be the length of the rod when it is in uniform velocity v. If the body moves with uniform velocity v relative to observer, then its apparent length is contracted by the factor under bracket 1 minus v square by c square to the power half in the direction of relative motion. That is L prime less than L. L prime be the length of the rod when rod is moving with uniform velocity v, and L be the length of the rod when rod is at rest. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and to subscribe my YouTube channel. Thank you.